All right, we're going to go ahead and get started with this month's PCAST talk. So before we do, we'll do a couple of announcements and then we will turn it over to our speaker. So a few bits of news from the project. So we're excited to have the volume 2 of the GEO book, the General Observer book, will be available soon on the archive. We're anticipating in early November. We received 120 submissions with many, many authors from many countries. Thank you again so much for everyone who participated in submitting a case and any editing that happened afterward. I think this is a really amazing publication that Ariel Moulet has been leading. PRIMA will be at the AAS in January, so there is going to be a PRIMA special session. It's going to be taking place on Wednesday, January 7th in the afternoon from 2 to 3:30, and everyone is invited and welcome. There will be contributed posters, and then there will be talks from various folks in the community on topics from galaxies to disks and everything in between. And we are still looking for folks to just remind us why you are so excited about PRIMA. So folks who are in our working groups, folks who are in the community, we have a form where folks can submit just some of their things that they're excited about. I'll put that link in the chat as well. But this is just a way for us to highlight, especially once we have the upcoming site visit this spring, just the real engagement that we've had from the community. And so finally, we have a few more upcoming talks for PCAST. We're quite booked all the way through the spring. So we have talks coming up from Kasia Judkowska, Grant Donnelly, and Meredith McGregor, who will all be speaking about their work from chemistry to high redshift pHs and then disks. So today, of course, we have Dylan Paré. So he's going to be telling us about one of my favorite topics, so the center of our galaxy, and looking at the magnetic field in this region and what we can do with ALMA, or with PRIMA. That we have started doing with telescopes like Sophia, and maybe a little bit of ALMA, and then these days what we can do in the future with PRIMA. So thank you.
Awesome. Yeah, thank you for the opportunity to give a PCAST talk. So let me share my screen. So are you seeing presentation?
Yes, looks great. Thank you.
Awesome. All right. So yes, I'll be talking a bit about the Galactic Center, specifically on the magnetic field aspect of this region, and the ways PRIMA can help refine our understanding of the magnetic field here. And so as a kind of an outline, I'll just give a brief overview of the Galactic Center, some of its properties, and then previous studies on what the nature of the Galactic Center magnetic field is, our current understanding of that field, and then end with the future prospects, particularly with an emphasis on PRIMA. All right, so what is the Galactic Center? So if we look at our Milky Way from face on, the Earth is located out in one of the spiral arms. I'm not sure if you can see my cursor. Does my cursor show up on the screen as well, or?
It's moving a little slowly. I think it has a bit of lag, but we could see it.
Okay, yeah, I think slow should be fine. So this red dot here roughly marks where the Earth is in the galactic disk. My cursor disappeared. There we go. And then the galactic center is at the very center of our galaxy. So it's about 8 kiloparsecs away from Earth, relatively nearby compared to a lot of other stuff you can study in astronomy. But one of the problems is that between the galactic center and Earth is the rest of the galactic disk. So we have spiral arms in the way, which leads to a lot of dust extinction. So if we look towards the galactic center in optical wavelengths, we see something like this. So we see a lot of extinction caused by intervening dust clouds. And so we're not really able to infer much about what's actually going on in the galactic center region in the optical. So what we need to do is go to non-optical wavelengths to kind of circumvent this extinction. And so this is an example taken of the very center of the galaxy. This is about 1 degree by half a degree field of view, which is a 3-color image in infrared and X-ray. So the yellow and red is infrared emission, tracing molecular structures, regions where there might be star formation. And then in the blue, we have higher energy X-ray emission, largely originating from high energy structures like the central black hole, which is in this area here, And then there's some X-ray emission associated with some OB star clusters like these spots as well. So you can tell that it's a pretty complex region with lots of different structures. We can also view the galactic center at radio wavelengths. So this is from the 1 gigahertz meerkat observation of the galactic center, where you can see a number of interesting structures. Like there are these filamentary structures, which I'll return to later in the talk. There are also these bubble type structures that are supernova remnants, and then numerous like H2 regions you can see throughout the galactic center. And just to orient you, that previous 3-color image I showed, the infrared and X-ray, covered about this field of view that I've marked with the box here. So this is a larger view of the galactic center, basically covering the entire GC region. And so what kind of structures do we see in the galactic center? So from the infrared, we see a lot of high density clouds throughout the region. So this is a column density distribution derived from the dust continuum, where we see a lot of high density clouds where structures like the Sagittarius B2 cloud have column densities of like 10 to the 23rd per cc, or per centimeter squared rather. And so these high density structures have come to be collectively known as the central molecular zone. And there's been a lot of work to study how these clouds are oriented in 3-dimensional space and what their velocities and motions through the region are. There's been a number of different models to try and figure out what the structure of the clouds are. So some of the models, like these two top models here, are open geometries where, for example, on the top left, the clouds are moving in like a 4 streams model. And then in this top right, it's a 2 spiral arm type model. So these are geometries that more connect to the galactic bulge and the larger galactic disk. Whereas other models have proposed more of a closed geometry, like the Molinari model, which is a twisted ring. And then this more recent model from this year, actually, of like a toy model ellipse. So there's been a lot of work this year by a group, by a number of papers trying to refine our understanding of the cloud distribution here. And they've settled on this upper left and lower right model, but it's still hard to distinguish whether it's an open or closed geometry for the cloud motion. So this is one area of active research on the clouds. Another aspect that complicates our understanding of the clouds within the GC is the fact that we see possibly multiple different dust populations in the region. So if we look at the cool dust, which we can get a sense of from Herschel 250 microns, so that's shown in the left figure here, we have a certain geometry or structure to the clouds. So this image here kind of reproduces that twisted ring structure that was shown in some of the models before. And this also agrees quite well with the column density distribution I showed previously. However, the warm dust, which can be probed by like the tens of microns wavelengths, show quite a distinct geometry. So we recover some of the same structures or similar structures to the cool dust, but we also resolve some new structures. Like there's these arches structures at the warm dust that doesn't have a prominent cool dust counterpart, for example. So this is another area where people are wondering how the warm and cool dust connects throughout the galactic center. There we go. And then one final question regarding this cloud population is the fact that we see a relative lack of star formation in the CMZ. So despite the fact that we have all of these high density clouds in the CMZ, we only have 10% of the star formation efficiency in the CMZ compared to what we would expect from extrapolating from the star formation rates in the galactic disk. And so this is quite a big discrepancy, and it remains unclear what the actual mechanism is that's inhibiting star formation. There have been a few proposed mechanisms, such as the elevated turbulence we see in the region, the high magnetic field strengths, or that the CMZ could be in a period of inactivity between more active star formation periods. So for the purpose of my talk, I'll focus more on this magnetic field aspect of this question, but there are other mechanisms that people are exploring and studying as well. Okay, so with that, I'll turn to some of the previous studies that have looked at the nature of the galactic center magnetic field. So I want to first talk about the radio side of things, and then we'll return to the infrared and the clouds in a little bit. So I showed this picture before of the Meerkat 1 gigahertz image, but I want to focus in particular now on these filamentary structures we see throughout the region. So these have come to be known as the non-thermal filaments because they emit non-thermal radiation. I've also marked the most prominent of the NTFs, which is known as the radio arc. One interesting thing about these structures is that they're so far only observed in the galactic center. There is no galactic disk counterpart to these structures, at least as of now that we can see. Oops, went the wrong way. And so because of the fact that they're only showing up in the galactic center, that has led us to wonder, what is it about the galactic center that enables the formation or illumination of these structures? And so there have been a few theories proposed here. One is that the non-thermal filaments could be connected to some sort of large-scale structure or event. So one example is from this 2019 paper, where they also with Meerkat, where they observed this large-scale synchrotron structure that's marked with this black dotted line. Excuse me. And most of the NTFs, which are marked in red, are confined within the structure, and some of them are even tracing the very edge of this structure, which they refer to as the chimney. So this could indicate that the NTFs are formed or illuminated by this material that's flowing out from the galactic center. And the thought is that this chimney could have been formed from a previous period of activity of Sagittarius A star or some previous starburst type event. But there is more layers of complexity here because a number of the non-thermal filaments are also seen near these sort of compact sources, a lot of which have X-ray counterparts. So this is an example from a study earlier this year where this non-thermal filament here has this compact source. And this is a radio image of this situation, but this compact source does have an X-ray counterpart as well. And so alternatively, the NTFs could be formed from more compact processes such as magnetic reconnection off of the surfaces of molecular clouds, or from electron diffusion as like a compact source, like a pulsar wind nebula passes through some magnetic flux tubes. And so given the range of non-thermal filament morphologies that we see in the region, most likely it's a combination of these compact and extended or large scale processes that's forming the NTFs overall. But it's still an open question about which of these mechanisms is the more dominant mechanism in forming these non-thermal filaments. And so some of the common properties of these structures is that they're highly polarized. Generally, their fractional polarizations approach the theoretical maximum of 0.7. And this image here is showing on the top panel the total intensity distribution of a representative NTF. And the lower panel here is its corresponding polarized intensity, where the polarized intensity is more patchy or discontinuous, but does generally trace the total intensity structure of the NTF. They also trace ordered magnetic fields, where the magnetic field is pretty much universally aligned with the orientation of the filament itself. So this is using that same example filament I showed before, where the contour level here is showing the total intensity extent of the filament, and then these black dashes indicate the magnetic field orientation. So if we then look at how the non-thermal filaments are distributed throughout the galactic center, this is a sketch showing the locations and orientations of the most prominent of the NTFs. They tend to be aligned perpendicular to the galactic plane. So the galactic plane is marked with this black dashed line here. So seem to all trace ordered magnetic fields. That seems to imply the existence of a large-scale vertical field in the galactic center that's oriented perpendicular to the galactic plane. But the picture becomes less clear when we turn to the infrared. So if we look at what the magnetic field inferred from dust polarization in the region is, we see a field that is pretty distinct from what we get from the non-thermal filaments. So I'm showing two examples here. On the right-hand side, this is an example of some magnetic fields obtained from warm and cool dust in the very central region of the galactic center. So this is the radio arc filament that I was showing earlier. And then this structure here is local to the central black hole of the galaxy. And then on the left-hand side, this is a zoom into a cloud known as the CMD, which is very local to Sagittarius A star, the central black hole. And we see a field system that doesn't generally connect with the non-thermal filaments, particularly this structure here. The NTF, or the radio arc magnetic field, tends to be along the filaments, but this structure shows a magnetic field that's perpendicular to that orientation. So it's not as clear-cut what the field orientation might be in this region. If we expand this out to looking at how the dust polarization magnetic field is throughout the CMZ, we see the same kind of picture here. So this is an example from PLO at 250 microns, where they looked at the dust polarization throughout the CMZ. So this color scale background shows the dust emission, and then this kind of wavy texture type feature indicates the orientation of the magnetic field inferred from the dust polarization. And so this field tends to be more aligned to the galactic plane, which is horizontal in this image, rather than connecting to the vertical field that's seemingly traced by the NTFs. And this kind of result was also seen with ACT-POL at 220 gigahertz. This is their result from that instrument as well. And it's a very similar field structure to what was seen with PLO. The field of view of that previous PLO image is marked with the box here. So even looking a bit outside the CMZ, you tend to see this kind of horizontal field system. Although one thing with the ACT-POL observations is that they have multiple frequencies that they observed with, and so their 90-degree observation starts to reveal possible connections with the radio arc. So this kind of field texture here actually coincides with the location of the radio arc NTF. And though there was no connection with the radio arc field at 220 gigahertz, there's indications of a connection here at lower frequencies. So this might start to give us some sense of how these field systems are connected. So there have been some theories on this question based on what we've seen so far. So one is that the vertical field that's seemingly traced by the NTFs could have been like the pervading field in the CMZ that then became sheared into a more horizontal orientation as the molecular clouds have started to collapse. And so that's what's shown in this diagram here, whereas the clouds begin to collapse, the field within the cloud becomes a more horizontal orientation. So that could explain a possible way that the radio and infrared fields are connected. Alternatively, the horizontal fields within the clouds could have been blown out into a more vertical orientation as a result of some sort of energetic process. So like a starburst or a previous activity from Sagittarius A star. And this connects with what we see observationally with structures like the chimney that seem to be these kinds of outflow structures as well. So there's evidence for either of these theories being true to reality. And so the question is, which one is more accurate? And that's still an active area of research here. All right, so then I'll just briefly go over our current understanding right now before going into our connections to PRIMA. So this was a recent study, the fireplace survey that was conducted using SOFIA HAWK Plus. We actually were able to get some of the last data from SOFIA before the observatory was decommissioned. So we were lucky because we almost weren't able to complete this map, but we were able to get in the last bit of data we needed to fully cover the CMZ. So this covers the entire CMZ region. And our resolution here of 19 arc seconds was chosen to match some of the individual cloud observations that were studied previously, while also improving on like the arc minute resolutions of the PLO and ACT pole observations from before. And so, so far, the study has resulted in 5 papers, some on presenting the data and some on analyzing specific molecular structures. So I'll just show what we get for the field throughout the CMZ. So if I zoom in, it'll be a bit easier to see. So the grayscale background here is the dust emission at 214 microns, which is the wavelength of fireplace observations. And then the orange dashed lines indicate the magnetic field orientation. So it's a much more spatially variant field than what was seen at either PLO or ACT pole. It does not have that uniform like horizontal orientation that was seen previously. It does tend to trace the orientation of molecular clouds within the region, however, but in lower density regions of the CMZ, the field does oftentimes exhibit a vertical orientation that might be connecting to the field inferred from the non-thermal filaments. And so this is easier to see if we histogram the polarization orientations we get from fireplace. So what we've done here is we've binned the polarization angle into 5-degree bins, and we recover 2 preferential field orientations. So this one peak here at about plus or minus 90 degrees, that connects to the field that is possibly traced by the NTFs, that vertical field. And then this other field component at around 15, 17 degrees connects to that field previously seen by PLO and ACT pole. So we seem to be recovering evidence for both of these systems. We can also look at how the field orientation changes with column density. So in this panel, I'm looking at only the lower column density regions of the CMZ, where we tend not to really see a significant parallel component, but we still have this vertical component that possibly links to the NTF field, where at higher densities, we get a more uniform distribution of polarization angle, and there's much more of a presence for that parallel field component. And I didn't show it here, but at the highest column densities for like the highest density clouds, the parallel component of the field comes through most strongly. So there is a column density dependence here on what we see with the field, which could help explain how these field systems are connected. So even with the fireplace observations, there are still a lot of questions left regarding the Galactic Center magnetic field and what role it could play in star formation. And so this is a really important area that PRIMA can enhance our understanding of. So what I'm really excited about for PRIMA is the polarimetric capabilities of Primature. With the decommissioning of SOFIA, we don't really have a way to study the infrared polarization, particularly at lower wavelengths. So what I'm showing here is the resolution and wavelength of the 4 Primature bands compared to some of the other observatories that have polarization capabilities or that will have polarization capabilities. So ALMA, for example, CCAP Prime. I've included the SOFIA HAWK Plus band that Fireplace observed with just for comparison. And so Fireplace was only the 1 color survey using the 1 HAWK Plus band. But with PRIMA, we have these 4 different bands to work with that allow us to probe the warm dust kind of at the 80s to 90s micron range. and then the cool dust at the 214, 215 micron range. And so that will allow us to build on the fireplace study in important ways. And so this is a figure demonstrating that utility. So on the top panel here is the distribution of cool dust in the Galactic Center. And I've included here various observations of the magnetic field for cool dust. So let me zoom in again. It might be a little easier to see. Yeah, so the blue dashed lines are the fireplace 214 micron that I showed previously. There's also 850 micron JCMT observations of some of the higher density clouds throughout the CMZ. And then there's some previous observations with Sophia and CSO as well. So the cool dust component, we have a pretty reasonable understanding of what the geometry of this field is, at least at this resolution. But when it comes to the warm dust, which I'm showing in the bottom panel here, our information is still quite sparse. So there are a few targeted studies of specific cloud structures at the warm dust. Like I mentioned, there's this arches structure in the warm dust. There's been some observations of that. The cloud near Sagittarius A star, the CND, there's some warm dust observations there. But in general, like throughout the CMZ, there's not a good sense yet of what the magnetic field is for this dust component and how it connects to what we see in the cool dust. So with PRIMA, we'll have the resolution to kind of match these previous observations, similar to what was done with fireplace, where the resolution was matched to some of these per cloud observations. So we'll be able to look at the structure of the warm dust field throughout the region for the first time with PRIMA, compare it with the cool dust as well. And so this is a observation kind of idea that we submitted as part of the as a JADIS case and also in the second science volume. And what's exciting is that we can observe the entire CMZ in all 4 premature bands using only about 3 hours of observation time. And I forget how many hours it took for us to get the entire fireplace field, but I think it was on the order of 30 hours, something like that. So an order of magnitude improvement in observation time there. And with PRIMA, we'll be able to actually get to a higher sensitivity than we were able to with fireplace. So even at the cool dust regime, we'll be able to probe into a bit more of the fainter structures in the CMZ than we were able to with Sophia. I guess that's one of the nice advantages of it being a space instrument instead of being in the atmosphere. Okay, and then there's a lot of synergies with our proposed observations and with some of like the future observatories and observatory upgrades that are coming up in the next decade or so. So with the ALMA wideband sensitivity upgrade, we'll be able to compare the field we obtained from PRIMA with ALMA. ALMA is able to give us arcsecond and sub-arcsecond resolutions. So we'll be able to study how the field structure changes over a range of spatial scales. And this kind of work is important because it allows you to assess whether the magnetic field is dominating in a particular cloud region or if some other mechanism like turbulence is dominating. So this is an example of this kind of multi-scale study done using the JCMT, KARMA, and ALMA. This is for a galactic disk structure, so not in the Galactic Center, but you can see how there's different field systems recovered at the different resolutions. And so doing this kind of work in the Galactic Center, there's been a little bit of work done on this using ALMA already, but the WSU will allow for an improved study of this, and then PRIMA will make for a powerful comparison for some of like the larger spatial scales with this kind of study. So that would be exciting to look at as well. Then with the NGVLA and SKA, these instruments more at the radio will allow us to get a better sense of the NTF magnetic field, which we can then compare with what we see from PRIMA to really study the extent to which there are connections between the infrared and radio fields. There are a number of NTFs that seem to coincide with molecular clouds, at least along the line of sight. So it'd be interesting to zoom in to those regions and see, do the radio and infrared magnetic fields at these possible points of interaction, do they connect or not? And then with the FIST survey from CCAT, this will probe more higher wavelengths than PRIMA. So combining our PRIMA observations with CCAT for the CMZ will allow us to do a comprehensive analysis of how the dust polarization changes with wavelength. And so these are just some examples of synergies with other observatories. There are some others as well. So I think I'll end the talk there. I'll put these references up if anyone's interested in following up on any of these. And I guess I'll open it up to questions.
All right, well, we're happy to take questions. You can go ahead and raise your hand or just speak out or put a question in a chat, and I'm happy to read it. Yes, question from Natalie. Go ahead.
Yeah, great talk, Dylan. I had a question on, I guess, the lower intensity sources that you had mentioned. So PRIMA is going to be able to push down the sensitivity to pick up some of these fainter structures towards the Galactic Center. So I guess my question is how will line of sight contamination impact these lower level sources? I know in Fireplace we were able to make the argument that because these sources were so bright, we could argue that the dust polarization was associated with CMZ sources. But if you're pushing the low level down, are you going to be impacted by line of sight contamination?
Yeah, that's a good point. I think we likely will for those fainter sources. Even, let me see if I can, yeah, so even, yeah, there we go. So even with Fireplace here, our thought when it comes to this like 15 odd degree component here is that likely connects with the field seen by PLO and ACTPol. But the thought is that the PLO and ACTPol field may not be exactly local to the CMZ, but might be a field component within the central KPC of the galaxy. So with the fainter structures from PRIMA, we will likely have more of a contamination from that field, but that will still be interesting information that we can use to verify, for example, our conclusions from Fireplace, whether this 20-degree component is some sort of foreground field or not. If we do see that systematically in the like fainter emission that we recover from PRIMA, that's a more definitive way to determine whether that's the case. So even if we do have more foreground contamination in those fainter regions, that'll still be a useful result to present. And then for the higher intensity, like clouds, whatnot, with PRIMA, we can still be confident that we're looking at more of the CMZ local field.
Great, thank you.
Mm-hmm.
So I'm definitely interested in any connections sort of between potentially a large-scale vertical field and a field parallel to the disk. Are there any particular sources or places that you might be looking to really target any such connection, whether it's maybe near Sagittarius star or whether it's in sort of the arches and infrared bubble area?
Yep. All right, let me go back to this image because it might be a bit easier to show. So right now, there are a few NTFs that we're looking at right now that coincide with molecular clouds. So this yellow is radio in this image here, and cyan is the cool dust. So this yellow structure here is a non-thermal filament that seems to go right through this cloud known as the 20 kilometer per second cloud. So right now, we're looking at like Fireplace compared to some VLA observations of the NTF. But it would be really interesting to follow up on this with higher sensitivity PRIMA observations of the cloud, and then something like NGVLA of the NTF as well, because we do
Right.
have some limits right now in what we're able to do with the VLA.
I mean,
There
that's a
are
particularly
also,
weird filament too, right? I mean, that one in
yeah.
particular like has an X-ray counterpart. There are
Mhm.
papers that are maybe not the most current that said maybe it's even the edge of a supernova remnant, right?
Yeah, so I was going to say that we're also interested in looking at these two. So there are these long filaments here that approach this molecular material, and then this arch as well for this structure. So they seem to maybe be originating from this molecular region, but then also extend out into these fainter regions where we don't have as much infrared emission. So these are structures we're also interested in looking at and could be good candidates to do this kind of PRIMA versus NGVLA type work to see how the field changes, say, along the lengths of these NTFs. Is there some dramatic change in the field structure once we overlap with the molecular material, for example? So this is perhaps a better comparison. And then the radio arc is always an interesting target. That's like my first paper from graduate school was on the radio arc. So I'm always interested in doing more studies of this like prominent NTF here. But yeah, so there are definitely a number of like NTFs that could serve as good targets for this kind of, exploring links between the infrared and radio.
What about filaments at, I mean, given like you have the non-thermal filaments, obviously, and there are
Mhm.
classes of other bizarre filaments that are seen at other wavelengths, and this is not necessarily a prima resolution question, although one can compare orientations. So like in the brick, some of the original observations of that
Mm,
cloud in the dust ridge with ALMA showed these absorption filaments, for example, in like HCO
mhm,
plus that were much less aligned. And I think there's been work recently with ALMA, very high resolution, also showing some more interesting sort of absorption filament. So how does one sort of make an overall model of what makes these linear structures on different scales in both the plasma and molecular field? And is this something that you think can be sort of overall unified, right, with an understanding of the whole magnetic field structure there?
yeah. I do. I think you're right that that will be complicated because you have all these different velocities in the region as well, and it's always difficult to figure out where does, say, the HCO plus absorption fall along the line of sight relative to the non-thermal filaments, right? So that's going to be the tricky part. I know there's been some recent work, like with Kara's group, on like the 3D CMZ stuff, looking at some of like the 3D geometry of like the molecular structures. But then where do the NTFs say, since they're not molecular structures, where do those fall in relation to that? So that's kind of the difficult thing, right? I mean, when it comes to the non-thermal filaments, we can say with reasonable confidence that they're in the galactic center region since we only observe them in the galactic center. But when it comes to placing them, say, like this filament here that you mentioned as well, like is this filament actually interacting with the 20 kilometer per second cloud, or is it just, happens to be there along the line of sight, right? So that is some of the work I'm trying to test with like the VLA observations I mentioned to see if there are systematic effects between the cloud and NTF when you get to like a crossing point. So like maybe if I zoom in, it's a little better. So like there's this portion of the NTF that's like outside of the cloud, right? So one aspect I'm working on with this VLA data is, do we see like a systematic brightness increase, or is there a systematic change in the magnetic field when you go from outside of the cloud to within the cloud? And so doing those kinds of observations can help you infer whether there's an interaction between these structures, which helps you determine whether they are co-spatial or not. So I think it's going to have to be a lot of work like that, which I think there has been some work done with the like some of the NTFs to try and infer that, but it's been a bit limited. And I think these next generation observatories like PRIMA and GVLA will definitely help with being able to refine our understanding there. But it is going to be a lot of work, and we're probably going to have to do a lot of like filament by filament and structure by structure type analysis to place this all into some sort of unified, comprehensive picture.
Cool, thank you. Any additional questions for Dylan? All right, if not, let's thank Dylan again. Thank you so much for talking to us about your work and some of the exciting promise of things that can be done with PRIMA. And everyone, thank you for joining us, and hopefully we will see you again next month. Take care.